Hello everybody, my name is Hristo Kolev. This is how you spell it, because sometimes I tend to mispronounce it and people get confused. So I have prepared for you a little presentation showing how do I communicate science and how do I teach science, because I'm a teacher and a science communicator as well. So I will start with the original scientific inspiration. Those are the famous American scientific communicators. Maybe you have heard about Richard Feynman. Well, he's a Nobel Prize laureate, but he's most famous for the Feynman lectures because he's such a good lecturer, such a good teacher, and he's very attractive, and people would want him to have documentaries and would want to see him on television talking about his passion in science and why physics is interesting. Another one, Carl Sagan, maybe you have heard of him. He's the founder, he's the father of the SETI project, the Search for Extraterrestrial Intelligence project. Very famous. And when I was little, or when I was younger, I used to be very much inspired by this film called Contact. It's a 1997 film. Maybe most of you remember it. Okay, I feel more comfortable with older audiences because normally my students don't know that film.
I know.
But that makes me feel young right now. So. Nice. So if you do remember that film, I'm not sure if you have noticed that the last frame of the film is actually a picture of the night sky and a sign to Carl. The reason is because that film was made by a book written by Carl Sagan. Unfortunately, he died a year earlier, so he couldn't see that film be up and running. But yet still he's a very famous science communicator responsible for a huge deal of scientific inspiration in the American public. And today we have Richard Feynman shouldn't be there. Today we have Neil deGrasse Tyson, the black guy. There's Neil deGrasse Tyson. Sorry about that mistake, I have no idea. Maybe I copied the text box and just left it there because it's actually not that easy to think of the spelling, Neil deGrasse Tyson. Yeah, okay, so it's Neil deGrasse Tyson. So he's a modern day science communicator, and he's very popular in America, but he's much more political, and he talks about the importance of science in society and politics and economics and all that. Of course, we have our own European stars, the stars of the BBC and the Discovery Channel programs. Maybe you recognize Robert Winston. Professor Winston is a biologist, and in my mind, in my eyes, he's most famous about his series about the human body, because I grew up with those, and my biology teacher would take all the class in this room where we had VCR and a huge television set, and we would watch his programs about the human body. So it's really exciting to see a science communicator, a true scientist that spends time in the lab, but takes some time to show, to raise the awareness of the public about science and science education and the significances of science for society. Brian Cox, he's a relatively young science communicator. He's 40 maybe, but relatively young yet still. Have anybody seen him? Does anybody know what is he famous for? He was part of a very popular rock band, actually. So he's a musician. He used to be a musician before he started his education in physics. So this is what he's most famous for. The group I believe, was called Dare. Maybe you have heard about the group, but not of him. It's Dare. Okay, never mind. Jamel Khalili is also a very popular modern-day science communicator. Britain, and most probably you have seen him in the BBC and the Discovery Channel programs nowadays. That's the group there. There they are. And that's Brian Cox. All right. The hair is a little bit different, and judging by the styling, I do believe they were an 80s or early 90s band. Yeah, maybe that's why you don't remember it, because it's almost 20 years. All right. So, as a Bulgarian science communicator, and Bulgarian science communicators through the British Council are trying to get this whole inspirational science communication thing from Britain here to Bulgaria, to our own radio, television, and stage. I happen to know the famous European science communicators, and this is me with Robert Winston. Yeah, Robert Winston. Okay, Robert Winston. In the Cheltenham Scientific Festival in 2010. It's a very popular, it's a huge scientific festival, and for 3 years now we have that scientific festival in Sofia, and we have it each and every year, and most probably we're going to have it next year. So everybody, all the teachers are welcome to come and see those European stars, the Bulgarian scientific communication stars, all the shows, all the inspiration, and all the beauty of science that is involved in such an amazing event that we have been having for 3 years. And this is Jamal Khalili and his lovely wife Julie. We made that picture sort of as a kind of a joke, because they really wanted to adopt me. But the problem is that you can't adopt anybody in Britain that is over 18 years of age. So yeah, that whole idea went to hell. So science communication, what is it all about? Well, science communication is about talking about the scientific inspiration and significance on stage, as acting as a stand-up comedian, for example, or a presenter, just like I'm doing right now, or being on television and showing television hosts what science is all about. And if you could get their attention, then the audience's attention will get there eventually. So basically this is all this thing is trying to get all that beauty from the laboratory into the television set, so that all the people can see it and all the people can wonder at it. And this is my inspiration. The quality is not that good of the projector, but those are my pets. Those are my fluorescent bacteria. That's a very special strain of bacteria that communicates using chemical signals. It's called quorum sensing. So basically what I take is all my experience, all my know-how in the lab, working with fluorescent molecules, working with spectra, working with molecular emissions, all that to show the beauty, what the beauty of science is all about. And quite recently, I had a new title. I became an artist, because in the scientific community, if the scientific community and the galleries say that you are an artist, it appears that you don't need to have an artistic education, and I don't, because I have a scientific education. And this is my very popular installation, or sort of a modern-day sculpture, called the Drosophila effect. Basically, that's a really massive object that has one Drosophila fly there in the center, and the laser ray is pointed at it so that it will be the center of attention, the center of this really heavy installation. It weighs about 35 kilos, and the Drosophila is about 1/5 of a milligram. So about 30 million, yeah, something like that, or 300 million. I'm not that very good with math. So see, it's better for me to stay in the gallery, not in the lab. All right, and I also do design that incorporates science, so that my scientific inspiration will be visible for people that have the eye to appreciate aesthetics. Another part of all that I showed you, all the know-how, all the scientific know-how that I use for is inventing new scientific demonstrations. I'm sure you have all seen the textbooks and the internet videos, the YouTube videos of the classical demonstrations about color, for example. And maybe many of you, are there any physics teachers here? Or is it just chemistry? Yes? There are physicists. Ah, that's nice. Okay. So, I'm sure that you have similar pictures in your, in the textbook that you're using to teach the science of color, right? Alright. So, I try to get out of that classical demonstration, or the colored wheel that spins and you get the mixture of colors and it becomes white, but it was colorful before it starts spinning, and take all that knowledge and all that beauty of the knowledge of colors and transform it into a beautiful new demonstration, if you will. So, because I'm a laser junkie, people believe that I'm a laser junkie because I really love all my lasers. But today I brought only 2. So, I hope you don't mind if I dim the lights. Yeah, that's better. Alright, so here I have my green laser. It's my 200 milliwatt green laser, and you can see the ray up in the chandelier, but the ray is also here and it's much thinner. I defocused it because when you're in television, everybody are really worried that you're going to set something on fire, so you have to be really careful with your lasers and defocus them. Alright, so basically all that I'm trying to show with that demonstration, it doesn't matter whether I show it in the classroom with my students, and I do it with my students, or on television, is basically the principle that a colored object would absorb the additional color. So the additional color for yellow would be blue. So yellow objects would actually, well, it's not blue, it's cyan, but it's magenta, but I really got confused, sorry about that. It's all about the language I'm using. Alright, so it's magenta. So magenta would be a mixture of green and, isn't it, cyan? So for the first time, for the second time, for the third time. The first time. Okay, so the first time. So I did this demonstration where I tuned the laser's power to be such that would let me pop balloons with different colors, depending on the absorption of their spectrum. So obviously, black object would absorb all the colors of the rainbow, all the spectrum. So if you put a black balloon inside, you should have expected that. It's not a big surprise, you should have expected that. Alright, so if you put a black object, then the molecules will start vibrating so vigorously that the balloon will heat up, it will melt, it will make a hole, and the balloon will pop. Well, it's not a difficult answer if I ask you what will happen with the white balloon. Well, white objects don't absorb any of the visible spectrum, so a white balloon would be safe in the ray of this green, 200 milliwatt by the way, in this 200 milliwatt green laser. Alright, this is where it gets interesting. I have a red balloon, and here everybody are starting to make assumptions whether it will pop or not. Well, let's see. The red balloon will actually absorb the blue and the green light, so using a green laser would eventually pop the balloon. And this is where it gets interesting. The blue balloon takes some time, or sometimes it fails because the color is not that intense, or sometimes you get a hole. Okay, so I will ask for my lovely assistant here on the first row to evaluate that there is a kind of like a scratch made by the laser beam, but the power is not enough. The power is not here. Okay, she confirmed it. See, I told you so. So the power is not enough for. Alright, see, it popped with the green laser. All right. So, this is where it gets interesting because I have a yellow and a green balloon. And maybe the most confusing part is the green balloon, but I'm sure that you already, all of you already know that the green balloon actually passes through green light. So it doesn't absorb green light, it absorbs the blue one and the red one. And the yellow one would absorb the blue light, right? So using a green laser, I can stand here like all day, but nothing will happen. It's almost just like the white balloon. All right. So let's spice things a little bit more. I have my newest scientific toy, and it's my 2-watt blue laser that I have delivered from the United States because apparently it's illegal to have such a powerful laser around here because just like standing here, I can just blind you all with science using that powerful laser. But I promise I'll be really, really careful. Okay, so I was hoping that I would have some volunteers to work with, some students to work with. So I would ask, I can see a beautiful young lady here, and maybe this young man here to help me show you just how powerful that blue laser is. All right. So here we have those black balloons, and I would ask you to stand here and align those balloons in one straight line. All right. Here they are. And maybe I would stand on this side. Can you see everything? Can you see the balloons? Or not too much? Alright. Now we're going to test just how powerful this blue laser is. Are you holding the balloons? Just don't get scared, alright? Okay. Ready? I'm not going to warn you. Or would you expect me to warn you? It's okay. Alright? The beam is running unfocused, so we need some time for the last balloons. Or maybe we'll never get them. You might as well just spare this one, alright? Okay, but as you can see, actually I'm not sure if you can see, but if I point it upwards on my black jacket, you can actually see the laser beam here because lucky enough, the room has enough dust particles to see the scattering of the light rays. So yeah, that's a really powerful laser, and it's really cool to demonstrate it with some smoke. But because I promised that I'm not going to have any dangerous chemistry today in this old room, I just thought that that would be a better idea just to demonstrate it like that. All right. The reason why I'm grabbing the presenter is because I forgot what's next. So, this was the balloon demonstration, and that's my favorite scientific toy, my radiometer demonstration. So apparently you can, it doesn't play. Alright, so maybe I should have used my computer. Alright, so it doesn't matter because I have the radiometer right here. The radiometer is a very popular desk toy, so that's basically one of those toys that you would see on the desk of some big shot businessman or some CEO of some company. Desk toys are very popular, and this is one of the most popular ones. So basically the radiometer looks just like a light bulb, but the pressure inside is decreased. It's not a complete vacuum. It's not a perfect vacuum. It's just a decreased gas pressure. And you have this little turbine inside it that would spin. But why that is? Well, very simple. The pedals of that turbine are colored, one side black and the other one white. So when light strikes the black molecules, they would absorb that light, they would heat up, they would start to vibrate. And when a gas molecule just flies by, that black molecule will kick that gas molecule the opposite direction. So there are really many things you can demonstrate that in the university, like for example, vibrational, electron vibrational energies of molecules. Or in high school, you can demonstrate momentum. Because normally people tend to speak about David Beckham kicking a football ball in zero gravity, and he kicks the ball this way, and he himself will fly this way. All right? But that's something you can use in high school or in secondary school demonstrations. And you can always point laser beam at it, and this is what I have here. It's not very interesting because it's dull and obvious, but it gets more interesting when you use magic, when you use something invisible, and this is what students are most inspired by, seeing the invisible. And in my mind, science is all about that. So here I have something, but I don't believe the table is close enough, so I'm going to move it here and use this regular light bulb that obviously makes up light, right? So now you see it, now you don't, because I found this really cheap vase on something like a dollar store or a Lev store around here. So this vase is actually made out of a special glass. This special violet glass would pass ultraviolet, maybe, but mostly infrared radiation, infrared light through, and it would hold the visible ones. So you could barely see the filament through it, actually. But I can feel the infrared radiation when I put my hand here. Well, I can't let you all feel it, maybe later, but when you're doing that with students, they can just put their hand and feel that there is something that their eyes are incapable of seeing. And this is just one small part of all the invisible world around us. So it's really inspiring for students to see that. So if I put that next to my radiometer, you will see that my radiometer starts spinning. And you can't actually see any visible light spinning it. You can, because it's reacting to the invisible infrared light. And if you get it closer, it will just go wild. Yeah, it will just spin faster. And if we had direct sunlight, we could demonstrate that direct sunlight has a lot of infrared radiation, and this is why we get so hot. Or you can go to a shawarma store, and because in the shawarma store they have this ceramic stove or something where they make the kebab. So this ceramic stove would actually emit a huge amount of infrared radiation, and you can normally feel it when you're waiting in line to get your food. So that's a really spectacular demonstration to show something invisible to students. That may be okay for students, but not for their parents. And maybe we all know that sometimes the problem is with parents that are too stubborn to let their kids study science or apply for a scientific program. And I had a case like that. So I got inspired to try and convince grown-ups, not just parents, but even young parents or future parents, grown-ups that are not in school anymore, that science can be really amazing and science can be really important for a country or a person or for a person's career. So what I made is this interactive installation. This artistic interactive installation has already been shown 2 places in Bulgaria already, and a third one is coming in September. So basically that's the infrared Mona. That's an invisible painting. Once you get into the gallery, you're going to see this kitsch frame, all right, because it's really kitsch. and this kitsch frame with a black silk canvas strapped in it. That's all that your eyes are going to see, because the image is infrared and your eyes are not sensitive to the infrared region of the spectrum. So the only way that you can see this small part of the beautiful world around you is to take out your cell phone of your pocket, turn on your camera, and the CCD matrix of the camera will do all the work for you, because it's a well-known fact that the CCD matrix of cameras are sensitive in the infrared region. And I have a personal rule not to show the image because it's an interactive installation and you really need to see it for yourselves, but this time I will make an exception. So this is the image that appears in front of your eyes on a cell phone display when you're looking at this blank black canvas. So it's really, really amazing for people to see that, to see this invisible beauty, as I may call it. And those are the audience. Okay, so we move to another inspiration of mine. I'm really keen on lasers and antiques. So there was this one time when I found, when I stumbled across, as you may say, this beautiful, beautiful antique Geiger-Müller tube. Can you see it from all those stuff? So this is the Geiger-Müller tube, this glass envelope here, the glass part of this contraption. So I just couldn't hold myself and I bought it because it's vintage, because it's an antique, because it works, it's functional, by the way, and I really, really needed to do all the schematics for the high voltage circuitry and the amplifier circuitry so that I can actually make it work, so that I can actually demonstrate it working and measuring radiation. So this is it. I brought it here. As you can see, I chose a transparent box. So basically you can see all the parts and I can tell you all about which one does what and why and how much and when. But the essential part, the heart of it, the vintage GM tube is visible as well. All right, so I haven't brought this to television yet, but sooner or later there will come this moment where I will show that on television, because you see, I don't know about other countries, I don't know about you foreigners here, but in Bulgaria people have a really wrong concept of radiation. They do believe that radiation is something created by those evil, evil scientists that try to kill us, to poison us, or to harm us in some other way. Well, actually radiation is something completely natural, and it's all around us, it's all in us, not just around us. So this is what I'm trying to, this is the message that I'm trying to get through. So I'm not sure if those headphones would be enough to hear the signal. Can you hear the clicks? Yeah. All right. Maybe I can turn on the speakers. Okay, I'll just shut up for a moment so that you can hear the clicks. How often do they occur?
That's cosmic.
Well, not just cosmic, but more like all around us, because I haven't opened the micro window. There is a micro window and I haven't opened it. There is this metal cap on it right now, so it's not cosmic yet. Okay, and this is another one of my favorite antiques. Does anybody recognize that? Has anybody seen an antique looking like that? It's a really strange, peculiar antique. It's from the beginning of the 20th century, but they used to do that in the 19th century as well. Okay, it's a small bowl that you can put some caviar, some jam maybe, and the aristocracy would have glassware like that. They would have glasses, they would have plates. So it used to be really, really expensive, so that only the aristocracy could allow that. And the reason is because it's really special, it's really beautiful. It's fluorescent. Right now I'm using my ultraviolet flashlight to show you that it's actually fluorescent. Well, the only way to make a fluorescent glass is if you put uranium in it. So that's uranium glass. And they don't do it anymore, not because it's dangerous and radioactive or stuff, because now we use uranium ore for something much more important than beauty and beauty pageants and aristocracy parties. We use it to make electricity. So we don't do those anymore because there is a really strict control over the uranium ore that it goes around. Okay, so basically what I have demonstrated to people and maybe my students is that if you can hear the clicks right now, that's the natural radioactive, what is the word? What is the English word? The radioactive? Background radiation. Yeah, that's the word. Okay, so if I put this uranium glass, this dangerous uranium glass ball here, you won't actually hear too much difference. A little bit, but not too much. Okay, so apparently it's safe. Okay, it's not just my opinion. Many people have tested it out, and it doesn't leak. It doesn't leak uranium into the food that you eat. So it's completely safe for people to sell in antique stores. So I moved from the invisible infrared region to the opposite region, the gamma region, because what you could hear right now were just the gamma rays. I didn't show you the alpha and the beta rays, but most probably there wouldn't be any because they can't exit a glass envelope. They cannot penetrate the glass envelope. All right, so I'm really bummed out about that. I can't play you the videos because here comes the ultimate inspiration, the Hollywood inspiration. So I'm going to try and play it like that. All right, here you see part of the second Harry Potter movie where they teleport to some other place using this magic powder, going into the fireplace and just saying the words, saying the address, if you will, saying the address where they need to go. So it's really, really impressive because they are just devoured by those huge green flames and they disappear and they appear on the second location where they need to go. All right. So, colorful flames, they have it in fireworks, yeah. And maybe you have demonstrated that in your classrooms using copper salts in the flame of a Bunsen burner or an alcohol burner, it doesn't matter. But it's not that impressive because one thing that I learned from my students is that the bigger the flame, the better. So I tried to think of a way to make this flame this big. And the way to do that is simply by, okay, maybe this one? Ah, yeah, here it is. So you need a big hard glass test tube and you need about 1 milliliter of methanol, not ethanol, methanol, and several crystals of boric acid. And when you heat it up, the esterification will take care of the rest, and then you can light up the fumes of the trimethyl borate that you get, and then you get this big flame. And if you have a dark room, if you have a room, a laboratory that you can put blinds on and you can make it darker, just like the laboratory that I teach in, it's really spectacular because all the room is just lit by this huge green flame. But keep it safe though, because you should use 1 milliliter of methanol at a time, because otherwise there is this chance that it will just boil up and you have even a bigger green flame, which is more spectacular, but it's not as safe. All right. So apparently I'm going to show you the videos this way. Sorry about that. I do realize that it takes a lot of time, but okay, so I talked about these desk toys. I showed you one desk toy, but I'm not only keen on desk toys, I'm keen on all other kinds of toys. So here's one more. And I'm really glad that we have a physics teacher. Okay. Yeah. It's not my water, so it's okay. So this little helicopter is just something that you can buy from any toy store. It's not considered a scientific toy, which is really strange for me, but for me it is a scientific toy. Well, the batteries are not fully charged, so this is why I'm having problems with lifting it up. But you already saw that it flies, so yeah. This is just a really cute little toy, but if you look at it closely, you will see that it doesn't resemble a real chopper or a real helicopter, because it has two propellers. And the reason is because in order to stabilize this little toy, you will need the two propellers to spin in an opposite direction. While this one spins clockwise, the other one will spin anti-clockwise. So this is something that you can use to teach about friction, because if there were only one propeller, it would spin around its axis because of friction. And then you have those weights here, those two little weights that are actually responsible for the gyroscopic stabilization of this little toy, which is not something that real helicopters have, or not too many of them. So yeah, this is another toy that I guess you could use in scientific education in physics. I'm really concentrated around physics because they wouldn't let me do chemical experiments here. So I hope that you're not too disappointed about that. Okay, another Hollywood inspiration. This is part of the film Practical Magic. Look at that. Did you see what she did there? Okay, I'm gonna play it again. I'm just gonna play it again so that you can see what happened. Okay. Okay, that's Sandra Bullock. Okay, she blows the candle and it catches fire. So, I don't lie to my students. I tell them that the Harry Potter effect is made by a computer. Yes, but you can do it in the lab. It's really spectacular for them to see that you can make something on a computer and do it live in the laboratory. But that was no computer. That was actually a real chemical demonstration that is too dangerous for this room, so I'm not going to show you right now. I'm just going to tell you. Yeah. That just bumps me out. But the way you do that is to take a piece of white phosphorus and to dissolve it in carbon disulfide. You need a high concentration, so don't spare the phosphorus. So once you have that solution, you can put a drop on the wick of the candle, and it won't stay there for that long. But when you blow it, you will make the solvent evaporate faster. And when the solvent evaporates, the left out phosphorus is pyrophoric, so it will ignite itself. And if you look at the movie closely, you will see that when she blows the candle, first you see a huge amount of white smoke, which is diphosphorus pentoxide, right? Or as it more common nowadays, tetraphosphorus decoxide, but never mind that. You know what I'm talking about. So that's actually not a computer-generated Hollywood effect. That's a practical science in a Hollywood movie. All right. So I can see that I have been talking for almost an hour, and you didn't say anything. I have just one little thing. Are you patient enough to see it? Okay. This is the demonstration that I used to get the candle into this room. All right. So this is my high voltage contraption. This is my high voltage contraption that I use on numerous occasions to scare students or television hosts, especially female television hosts, because apparently they find high voltage scary. And it is scary, but I always say one thing: it's not the voltage that kills you, it's the amps. So if you keep the amps low, then everything will be safe and everything will be okay and nobody will be harmed. And no television equipment will be lost. Just to show you how high voltage do I have here, I'm just going to show you what the spark looks like. Alright? We have a physicist in the room. How many volts do you believe that is? Judging from the size.
5 or 6.
5 or 6 what?
1,000.
1,000. Oh, sorry, it's much higher. It's 40. You were close enough. It's 40,000 because there's a really simple practical rule. For 1 centimeter spark, you get 10,000 volts. So about 4 centimeters, it's 40,000 volts. Okay, so now I'm going to connect this high voltage wire to this tin can here, although I call it my electrode, and the ground wire will be connected to this one. So basically, I'm going to put the candle flame inside this really, really intense electric field and see what happens. Okay, they're not close enough. Okay, you can start to see the effect. You can start to see the flame actually splitting into 2 parts horizontally, right? Can you see that? It goes horizontally. I'm afraid that we're going to get a spark if I get them close enough. Okay. So now there are these moments where you can see the two parts of the flame. And this is because of the gas ions. There are gas ions, positive and negatively charged ions, inside the flame. So when you ask what are the essential ingredients in a romantic dinner, you would get a glass of wine, good food, nice music, and several gas ions. And as you can see, because the flame is conductive, we got a spark because it decreased the resistance of the air between the 2 electrons. So it's a really, really nice demonstration to show the chemistry and the physics of a romantic dinner. Okay, so I'm going to stop right here.